For as long as humans have looked up at the night sky, they have wondered whether the universe goes on forever or has an edge. Modern cosmology offers clues but not a final answer, and thinkers like physicist Brian Cox have helped frame these questions with calm clarity and wonder. Tonight we take a quiet journey through what science knows what it suspects and what still lies beyond our reach when we ask whether the universe is truly infinite. If you enjoy gentle trips to the edge of space and time, please like, subscribe and share, and tell us in the comments what is your favourite unanswered question about the universe. Thank you for watching. Now let's begin. The story of the observable universe begins with a simple fact. Light takes time to travel. Every distant galaxy, every faint glow in the background of the sky, sends out light that spends vast stretches of time crossing space before it arrives at a telescope on Earth. This delay turns the night sky into a map of distance and of age. The farther away an object is, the longer its light has been in flight, and the further back in cosmic history it reveals. In this way, astronomers define a visible region around Earth, a kind of sphere in which light has had enough time to arrive during the finite age of the cosmos. This sphere is called the observable universe. Its size is not guessed. It is inferred from the measured expansion of space from the motion of distant galaxies, and from the faint afterglow of the hot early universe that still washes across the sky. Within this sphere, light has had time to cross the growing distances between galaxies and star clusters, and reach instruments placed in orbit and on the ground. Beyond this sphere there are regions whose light has not yet had time to complete the journey. They may exist and may be full of galaxies and stars, but they remain outside the reach of observation today. The observable universe is therefore not a true boundary of the cosmos. It is a boundary of information set by the finite speed of light and the finite time since the hot, dense state usually called the beginning. When astronomers say that the observable universe extends for tens of billions of light years in every direction, they are describing the present distance to the most remote objects whose light has just managed to arrive. The numbers involved are extreme, but the idea remains straightforward. Take a universe that has been expanding for a finite time. Let light move through that expanding space at a fixed speed. Then there will be a largest distance from which light could have reached Earth by now. Everything inside that distance forms the observable universe. Everything beyond lies outside the current horizon of sight, not because it is cut off by a wall, but because the signals have not yet arrived. This picture is already striking, yet it also introduces a deeper question. If only a finite region is visible, how large is the region that is not visible? The sample of the universe that can be directly mapped includes hundreds of billions of galaxies each, with hundreds of billions of stars. Deep surveys that stare at apparently empty patches of sky for days or weeks reveal that those patches are not empty at all. They're crowded with remote galaxies, some so distant that their light began its journey when the solar system did not yet exist. From these surveys, astronomers count galaxies in a small region, estimate how typical that region is, and then extend the count across the entire observable sky. The result is a picture of a cosmos that is already vast beyond everyday comprehension, yet still described as only a piece of something larger. The edges of this mapped region do not look like edges in any familiar sense. There is no thinning of galaxies, no abrupt drop in structure, no visible sign that space itself is running out. Instead, the distribution of galaxies appears broadly similar across the sky, with large-scale structures and voids continuing out as far as current instruments can trace them. When a map of the observable universe is drawn, its outer boundary is not a physical shell. It is a marker that says that beyond this distance the light has not yet arrived. For a viewer who imagines floating near that limit, the scene would look much the same as it does from Earth. Galaxies would still fill the sky in all directions. the local region would still sit at the centre of its own observable sphere, and nothing in the view would reveal that the horizon had been reached. This is one of the quiet but profound features of cosmology. Every observer, wherever that observer may be, sits at the centre of an observable sphere defined by the same rules of light and time. No location is special. The apparent centre is simply the place from which distances are measured. In a universe that looks roughly the same in every direction on very large scales, each point sees itself surrounded by a similar horizon. The existence of this horizon carries a subtle message about questions of infinity. The fact that the observable universe is finite in volume and in age does not by itself tell whether the whole of space is finite or infinite. The horizon shows the current limit of evidence, not the limit of existence. A finite age means that only a finite portion of space can be observed so far. It does not set an upper bound on how much space there is in total. Even if space stretches on without limit, only a finite region can ever have sent light to a given place by a given time. From this standpoint, the observable universe is best seen as a window cut into a much larger structure. The size of the window grows as time passes and more distant light arrives, yet there is no guarantee that the frame of the window will ever encompass the whole. This sample script that speaks of a universe tens of billions of light-years across already hints at this. It describes a region that is immense yet clearly incomplete, and it notes that the farthest edges do not resemble an end. Modern maps reinforce this impression. They show filaments and clusters of galaxies stretching to the edge of the plotted volume, as if the pattern simply continues beyond the drawn circle. This leads naturally to speculation. If the view today reveals no sign of a boundary, and if the laws of physics appear to be the same in every direction at large scales, then it is reasonable to wonder whether the cosmos goes on far beyond the visible shell, perhaps without end. At the same time, the simple presence of a horizon is a reminder of restraint. There may be regions of space that are forever beyond contact. Their light will never arrive because the expansion of space carries them away faster than light can bridge the growing gap. Those regions, if they exist, may share the same broad properties as the observable universe, or they may differ in ways that present theory can only hint at. In this first step of the story, the task is not to decide which of these possibilities is true. It is to understand clearly what is meant by the observable universe, why its horizon exists, and how this horizon leaves open the deeper question of whether space beyond it ends, bends back on itself, or stretches on in a way that never runs out. In order to understand how large the observable universe really is, astronomers do not begin with the whole sky at once. They begin by choosing very small regions that at first glance appear almost empty. A telescope in orbit free from the blur of Earth's air is pointed at a patch of darkness between the bright stars of the Milky Way. The telescope is left to collect light for many hours and then many days. With each passing hour, extremely faint signals accumulate. The final image reveals that the patch of apparent emptiness is full of distant galaxies. What looked like a blank region becomes a crowded field of tiny shapes and colours. Almost every point of light in that deep image is not a single star, but an entire galaxy containing many billions of stars. One famous image of this kind, often described as a deep field view, shows over 10,000 distinct galaxies in a region of sky so small that it could be covered by a grain of sand held at arm's length. Each of those galaxies is a system of gas-dust stars and dark matter. Many contain hundreds of billions of stars. Some are much smaller. Some are already fully formed in the early universe, others still in the process of assembly. From such an image, the idea of counting galaxies across the entire observable universe begins. The method is simple in concept. First, a deep map is made of a tiny area, and the number of galaxies in that area is counted down to a certain limit in brightness. Then similar counts are made in several directions across the sky. The counts are corrected for known biases such as dust in the Milky Way that can hide some galaxies, and for the fact that so many become too faint to see beyond certain distances. Finally, the average number of galaxies per small patch of sky is extrapolated across the full area of the celestial sphere. The outcome is not a single exact tally, but a range. Current estimates suggest that the observable universe contains at least hundreds of billions of galaxies, and perhaps close to 1 trillion if very faint and small systems are included. Each galaxy in turn may hold on average something like 100 billion stars. These numbers shift as instruments improve, but they remain consistently enormous. In this way, a finite sky yields counts that already feel close to endlessness. At the same time, the method exposes its own limits. It always involves assumptions about how typical a surveyed patch is, about how many objects lie just beyond the threshold of detection, and about whether there are whole populations of galaxies that current telescopes still miss. Astronomers try to reduce these uncertainties by surveying many independent directions, and by comparing data from different instruments and wavelengths. Sky surveys that cover large areas at moderate depth, such as long-running projects that measure positions and distances for millions of galaxies, complement the deep but narrow pencil beam views. Together they build a three-dimensional map of the matter in the observable universe stretching out over billions of light years. This map reveals a cosmic web of clusters, filaments, and vast empty voids. It shows where galaxies gather under the pull of gravity and where they are scarce. Yet even as this structure becomes clearer, nothing in it points to a sharp wall or an outer edge. The density of galaxies varies from place to place, but there is no sign that large regions are missing no visible thinning that signals the end of space. The finite sky that humans can map therefore feels much larger than any everyday experience suggests, yet still behaves as if it were a representative portion of a wider pattern that continues beyond view. The deep images and wide surveys also help to anchor more abstract statistics. From them, astronomers estimate not only how many galaxies exist in the observable universe, but also how many stars, how much ordinary matter, and how much dark matter must be present to generate the observed motions and clustering. When these numbers are combined with measurements of the cosmic microwave background, the faint afterglow of the early hot phase, a coherent picture forms. It is a picture of a universe that is homogeneous and isotropic on very large scales, meaning that when averaged over great distances it looks broadly the same in all directions and in all locations within the observable patch. This uniformity is one of the reasons why extrapolation feels justified. If every region that can be observed on the larger scales displays similar properties, it is natural to suspect that regions beyond the current horizon share those properties as well. In that case, the counts obtained from deep surveys would be valid not just locally, but across volumes of space that far exceed what any telescope can directly probe. The thought immediately raises the question of total size. If the same pattern of galaxy distribution continues indefinitely, if there are always more clusters and filaments and voids beyond each surveyed shell, then the total number of galaxies may not just be large but unbounded. An infinite universe filled with galaxies of roughly the same average density would contain infinitely many galaxies and infinitely many stars. Yet the data themselves do not require such a conclusion. They show that within the observable volume, the universe behaves in a way that is consistent with a larger homogeneous whole. They do not reveal how far that homogeneity extends. There could, in principle, be a very large but finite region beyond the horizon where conditions change, or where the fabric of space takes on a different global shape. The counts of galaxies therefore serve a dual role. They emphasize how much structure and variety is already present in the finite sample that can be mapped. At the same time, they highlight how little that sample says about the ultimate extent of everything. An observer standing on Earth can look at a deep field image and know that each tiny patch of sky hides thousands of galaxies, and that the whole dome above is filled with such patches. From this alone, the mind is pushed toward a sense of something that almost feels infinite. But the careful use of the word almost matters. The sky that is catalogued and counted remains a finite construction. It is large, detailed, and rich, yet bounded by the limits of time-light and instruments. Beyond its edge lies a region that is not observed. Whether that unseen expanse is merely more of the same, or whether it contains different structures entirely, is an open question. In this second step of the narrative, the act of counting becomes more than an exercise in statistics. It becomes a way of confronting the gap between what is measurable and what is imaginable. The numbers drawn from the finite sky are solid anchors for any discussion of infinity. They show what is definitely there. They also invite the possibility that the pattern continues without end, while reminding that such an extension remains for now an inference and not a measured fact. In this tension between the secure counts of galaxies and the unknown realm beyond the horizon, the question of whether the universe is truly infinite begins to take on sharper form, even though it still has no final answer. The picture of a finite observable universe rests on measurements of expansion and age. Long before space telescopes exist, astronomers notice that many faint smudges in the sky are not clouds of gas in the Milky Way, but separate galaxies far beyond it. As instruments improve, spectra reveal that the light from most distant galaxies is shifted toward longer wavelengths. This redshift is interpreted as a sign that space between galaxies is stretching. In the language of general relativity, which describes gravity as the curvature of space-time, the simplest large-scale solutions for a universe filled with matter and radiation involve either expansion or contraction. Observations show expansion. The greater the distance to a galaxy, the greater its measured redshift on average. This relationship allows astronomers to treat galaxies as traces of the overall growth of space. By measuring how quickly galaxies recede at various distances, they infer how the scale of the universe changes with time. When this behavior is traced backward, the distances between galaxies shrink. The large web of clusters and filaments that fills the observable universe today becomes denser and hotter in the past. Extrapolated far enough, the model leads to an early state in which matter and radiation are packed into a volume that is smaller and hotter than anything seen since. This is the hot Big Bang phase. It is not described as an explosion inside an existing empty space. Instead, it is a period when space itself is much more compressed, and the energy density is extremely high. The relic glow of that hot phase, the cosmic microwave background, is still present as a very faint radio-like light that fills all directions in the sky. Its spectrum and small variations confirm that the universe has indeed expanded and cooled from a past state of great density and temperature. From these data, combined with measurements of the present expansion rate and the content of matter and dark energy, astronomers estimate the age of the universe. Current analyses place this age at about 13.8 billion years. This number represents the time that has passed since the hot, dense phase became describable by the smooth expansion model used in modern cosmology. It is a specific, finite duration. From the standpoint of everyday intuition, a universe with a finite age might seem likely to be finite in size as well. If the story has a beginning, perhaps space itself starts at a point and grows outward into some larger emptiness. The actual situation suggested by general relativity and by observations is subtler. The equations that describe expansion relate the rate at which distances grow to the average density of matter radiation and dark energy, but they do not directly fix the total size of space. They can be applied to a cosmos that is spatially finite, like the three-dimensional analogue of the surface of a sphere, or to one that is spatially infinite, like an endless flat plane extended into 3 dimensions. In both cases, if the contents and initial conditions are similar, the local history of expansion can look the same. A finite age tells how long the scale factor, the quantity that measures the relative stretching of space, has been increasing. It does not say whether that stretching acts on a region that is large but bounded or on one that has no bounds at all. Another way to see the same point comes from considering horizons. Because the universe has a finite age and light travels at a finite speed, there is a maximum distance from which signals can have reached any given location. That distance defines the observable universe. It is larger than the simple product of age and light speed because while the light is in flight space itself continues to expand, increasing the separation between source and observer. The result is that the present distance to the farthest galaxies whose light is just arriving can be many tens of billions of light years, even though the light has been travelling for only about 13 billion years. Beyond that distance, there may be more of the same kind of space and more galaxies. The age of the universe does not place a direct cap on how far space extends. It only limits how much of that space can be in causal contact with a given point by a given time. In this framework, the initial hot phase is better thought of as a moment when all regions that can now be seen were once much closer together, rather than as a moment when everything begins from a single point in ordinary three-dimensional space. General relativity even allows solutions in which the hot Big Bang is not the absolute beginning of the universe, but only one phase in a longer history. Some inflationary models, for example, describe a pre-existing state in which a region of space undergoes a brief rapid acceleration before settling into the more gradual expansion observed today. The details of such scenarios belong to later parts of the story, but even their existence as possibilities underlines a key idea. A finite age for the hot, dense state does not necessarily mean that the universe as a whole, in all its spatial and temporal extent, is finite. What the data show securely is more modest and more precise. They show that for roughly the past 13.8 billion years, the part of the universe now observable has been expanding and cooling in a way that matches the predictions of a homogeneous isotropic cosmological model. Within that model, distances between clusters of galaxies have grown by large factors. Radiation that once had the spectrum of a very hot source has been stretched to much longer wavelengths. Density contrasts that began as tiny irregularities have amplified under gravity to become the present cosmic web. All of this unfolds within a framework that does not yet reveal whether the underlying spatial manifold is finite or infinite. The question of infinity remains open because the expansion history derived from observations describes how space behaves locally and over time rather than how far it reaches. In this third step of the narrative, the measured age of the universe and the evidence for expansion place firm bounds on what can be said about the observable region. They set a clock that has been ticking for a known duration. They define a light horizon that grows as time passes. They show that the cosmos has evolved from an early hot and dense state to the present structured and relatively cool state. But they stop short of answering whether the stage on which this history unfolds is a finite arena or an endless expanse. That deeper question depends on global properties of space that current observations only begin to probe, and it is to those properties that the discussion must next turn. The question of whether the universe is finite or infinite is closely tied to the question of its shape. On everyday scales, space feels flat. Lines appear straight, surfaces seem level, and the rules of geometry learned in school seem to hold without exception. On cosmic scales, however, general relativity allows space to be curved by matter and energy. The overall geometry of the universe can be positive, like the surface of a sphere extended into 3 dimensions, negative like a saddle shape, or very close to flat like an ideal plane. Each of these possibilities carries different implications for how far space extends and how it behaves on the larger scales. To study this geometry, cosmologists use the cosmic microwave background as a kind of distant reference pattern. This faint radiation left over from the early hot phase last interacts with matter when the universe is a few 100,000 years old. At that moment, matter and radiation are tightly linked, and small variations in density imprint tiny temperature differences on the radiation. These temperature fluctuations form a pattern across the sky that encodes information about the contents and curvature of the universe. The distance to the surface from which this radiation last scatters, together with the way light travels through the intervening space, determines how large the features in that pattern appear. By measuring the apparent size of characteristic features in the cosmic microwave background, satellites can infer the underlying spatial curvature. If space is positively curved on large scales, like a three-dimensional version of a sphere, straight lines that are initially parallel tend to converge. A triangle drawn along the shortest paths between three distant points has angles that add up to more than a straight line. In such a universe, the total volume of space can be finite even though there is no physical edge. If space is negatively curved like a three-dimensional version of a saddle, straight lines tend to diverge, and the angles of a large triangle add up to less than a straight line. In that case, space can be infinite, and its geometry affects how structures grow and how light propagates. If space is flat, the large-scale geometry obeys the familiar rules of Euclidean geometry, with the angles of a large triangle adding up to a straight line. In this case, space can be infinite, but it is also possible to construct topologies in which a flat space is finite yet unbounded by identifying opposite faces of a large region. Precise maps of the cosmic microwave background made by missions operated by space agencies show that the universe is extremely close to flat on the largest observable scales. The data indicate that the total energy density of matter radiation and dark energy is extremely close to the critical value required for flatness in the standard cosmological model. The allowed deviation from perfect flatness is very small. Within current measurement, uncertainty space could be exactly flat, or it could be slightly positively or negatively curved with a very large radius of curvature. In practical terms, this means that if the universe is curved, this curvature is so gentle that it would take regions far beyond the observable horizon to trace it clearly. This result has profound implications but does not by itself decide the question of infinity. A universe that is perfectly flat in the simplest models is most naturally infinite in spatial extent. It stretches without end in all directions with no special center and no physical boundary. However, flatness does not logically force infinity. Certain topologies allow a flat universe to be finite yet unbounded, much like how the surface of a cylinder can be flat locally, while looping around on itself in one direction. In such models, travelling far enough in a straight line could eventually return an object to its starting point, even though local geometry remains Euclidean. The observation that space is nearly flat therefore leaves several options open. It supports the idea that the universe is at least much larger than the observable patch, because significant curvature over that patch would have produced clear distortions in the cosmic microwave background pattern. It suggests that if the universe is finite, its total size must be many times larger than the part that can currently be seen. It also makes an infinite universe with uniform properties a simple and attractive possibility. Yet none of these options can be singled out as proven solely from the curvature measurement. The flatness result also connects back to theories of the early universe. Inflationary models which describe a brief period of rapid accelerated expansion shortly before the hot Big Bang phase naturally produce a universe that appears very flat within any finite observable region. In these models, space is stretched so much that any initial curvature becomes undetectably small over the scales that can now be observed. This provides a compelling explanation for why the measured curvature is so close to zero. At the same time, inflation often predicts a total universe that is vastly larger than the observable patch, and in many versions effectively infinite. The combination of an almost flat cosmic microwave background and the success of inflationary ideas in explaining other features of the universe, such as the origin of structure, encourages the thought that the cosmos might be enormous beyond direct observation, perhaps even without bound. Still, a cautious view is important. The data show that within the observable universe on scales approaching the horizon space behaves as if it were flat. This behavior fits neatly with a universe that is either extremely large and finite or infinite. It does not reveal which is correct. Attempts to detect signs of a finite topology, such as repeating patterns or matched circles in the cosmic microwave background that would arise if light had wrapped around the universe more than once, have so far yielded no clear evidence. The absence of such patterns places lower limits on the possible size of a finite universe, pushing it far beyond the radius of the observable region, but it does not rule out finiteness entirely. In this part of the story, the shape of space emerges as a subtle but crucial element in the infinity question. A universe with strong positive curvature would naturally suggest a finite volume. A universe with strong negative curvature would favour infinite extension. Instead, observations point to a case balanced very close to flatness, where the simplest reading of the data suggests an enormous or infinite cosmos, yet alternative, finite yet vast shapes remain possible. The measured flatness therefore acts as a kind of fork in the path. It narrows the possibilities but does not end the debate. It says that if the universe is finite, it is far larger than the horizon. If it is infinite, the observable region is only a tiny fraction of the whole. The task then becomes to explore other properties of the universe, such as its topology and its early inflationary history, to see whether any additional clues can be found. For now, the flatness of space stands as one of the strongest hints that the universe might be much larger than the visible sky suggests, and perhaps limitless, while still leaving room for a finite but edgeless cosmic shape that current instruments cannot distinguish from true infinity. When cosmologists consider the possibility that the universe might be finite yet without edges, they turn from curvature to topology. Curvature describes how space bends locally under the influence of matter and energy. Topology describes how space is connected on the larger scales. Two spaces can share the same local curvature and yet differ in their global connections. This distinction allows a universe that feels flat in every small region to be either infinite or finite, depending on how its large-scale structure is stitched together. To picture this, one can imagine a simple two-dimensional example. A flat sheet that extends without limit is both flat and infinite. A different construction takes a rectangular patch of flat sheet and identifies opposite edges so that moving in a straight line off one side brings an object back in on the other side. The surface remains flat everywhere locally, yet it is now finite and has no boundary. In 3 dimensions, similar constructions exist. A flat 3-dimensional space can in principle be arranged so that travelling in a straight line eventually returns an object to its starting point, even though no edge is ever encountered. In such a universe, light could wrap around the cosmos, passing through the same region multiple times along different paths. The idea of a multiply-connected universe grows from this kind of reasoning. A simply connected space is one in which any closed loop can be continuously shrunk to a point without leaving the space. A multiply-connected space allows loops that cannot be shrunk in this way, because the global structure forces them to wind around some non-trivial feature. In cosmology, a multiply-connected topology could mean that the observable universe is only a small fundamental region of a larger repeating pattern. The actual total volume might be finite with the pattern tiling space in a way that repeats beyond the horizon, or it might be infinite but composed of repeating cells. Observationally, this would leave delicate traces. If the universe were small enough, and light had had enough time to traverse it more than once, an observer could in principle see multiple images of the same distant object in different directions. The cosmic microwave background would also carry a signature. Light that last scatters from the hot early plasma could circle the universe and intersect itself, producing matching patterns in the temperature fluctuations across different parts of the sky. Researchers have searched for such repeating patterns, often described as correlated circles in the cosmic microwave background. These searches look for pairs of rings with the same sequence of hot and cold spots shifted and rotated that would signal light arriving along different paths from the same physical region. So far, no convincing evidence for such matched circles has been found. This absence is informative. It implies that if the universe does have a non-trivial topology that causes space to loop back on itself, the characteristic size of that topology must be larger than the observable region by a significant factor. Otherwise, the predicted repetitions would be visible. The lack of such signs therefore pushes any finite topology outward. It suggests that if space is finite, its global scale is so large that the observable universe fits comfortably inside it without significant self-overlap. In that case, the local sky would be indistinguishable from the sky in an infinite flat space, at least with current instruments. Galaxy surveys provide a complementary line of evidence. If space repeats itself on scales comparable to or smaller than the observable region, there could be multiple copies of the same large-scale structure. The same pattern of galaxy clusters and voids might appear in different directions at different redshifts with characteristic relationships. Detailed mapping of the three-dimensional distribution of galaxies has not revealed any clear repeated patterns of this sort. As with the cosmic microwave background, this lack of repetition sets lower bounds on the size of any fundamental repeating cell. It does not rule out a finite topology. It simply indicates that if such a topology exists, the corresponding size is well beyond the current horizon of observation. In this way, topology plays a quiet but central role in the infinity question. A universe with a simple, infinite, flat topology is conceptually straightforward. Space extends without limit. Any finite region, including the observable universe, is just one small part of an unbounded whole. A universe with a finite multiply-connected flat topology is more subtle. Space has a limited total volume but no edge. Every path that seems to go outward eventually returns, though perhaps after distances so great that light has not had time to complete the circuit since the hot Big Bang phase. For inhabitants of such a universe, the observable sky can look exactly like the sky in an infinite universe if the fundamental scale is large. On scales smaller than that, scale distances, angles and structures behave in the same way. Only on scales comparable to the fundamental size does the looping become apparent. General relativity itself does not choose between these possibilities. The equations allow a wide range of topologies as long as the local geometry satisfies the field equations with the given matter and energy content. The standard cosmological model usually assumes the simplest case as space that is either infinite and flat or finite, with constant curvature and simple connectivity. This assumption is made because it is mathematically economical and fits available data. But from the standpoint of pure theory, more complex topologies are equally allowed. The decision between them is empirical. It depends on what the sky reveals. The current situation can be summarized in cautious terms. Measurements of the cosmic microwave background and galaxy surveys show no strong evidence for a small finite topology. They are consistent with a universe that is either infinite or finite, with a characteristic scale much larger than the observable region. The data set lower limits on that scale, often quoted as many times the radius of the observable universe. These limits shift as analyses improve, but the qualitative conclusion remains the same. If space loops back on itself, it does so on scales too large to be directly detected so far. For the question of infinity, this means that topology does not yet provide a decisive answer. It offers a framework in which an apparently flat universe can be finite without edges, but the universe might also be truly infinite. Both options are compatible with current measurements. What topology does supply is a conceptual tool. It shows that finiteness does not necessarily require a boundary. It opens the possibility that space can be limited in volume yet seamless, with paths that eventually return without meeting a wall. In this sense, topology softens the contrast between finite and infinite. It allows a universe that is finite but so large and smoothly connected that on any reachable scale it mimics infinity. The observable universe then becomes a small patch within a larger structure whose full form is hidden, whether that structure is endless or loops back on itself in ways that light has not yet had time to reveal. In the unfolding narrative, topology adds one more layer to the puzzle. The cosmos can be curved or flat simply, or multiply connected, finite or infinite, and present evidence does not yet pin down which combination nature has chosen. The only firm statement that can be made from this angle is that the space within the observable universe behaves as if it belongs to a larger whole that extends well beyond the visible horizon. Whether that whole finally closes upon itself or stretches on without limit remains an unanswered question that the next stages of cosmological investigation continue to probe. In the story of how large the universe might be, inflation occupies a central place. Inflation is the name given to a brief period of extremely rapid expansion, very early in cosmic history. In many models, it occurs just before or at the very earliest stages of the hot dense phase that later becomes the familiar Big Bang picture. During inflation, the scale of space does not merely increase steadily as it does now. Instead, it grows at an accelerating rate, doubling again and again in a tiny fraction of a second. This rapid stretching has far-reaching consequences for the size, shape, and uniformity of the universe that can be observed today, and for any regions that lie beyond the horizon. The idea of inflation arises from attempts to explain two key features of the observable universe. The first is its large-scale smoothness. Maps of the cosmic microwave background show that aside from tiny fluctuations, the temperature is almost the same in every direction. Regions that are widely separated across the sky today would have been far apart even in the early universe, too far for light or any other signal to pass between them in the time available before the hot plasma cooled and released the radiation we now see. Yet those regions share almost identical conditions. Inflation offers a way to explain this. If before the hot phase, the part of the universe that later inflates is small enough for all of it to come into close contact, then physical processes can smooth out differences and bring it into near uniformity. When that region then undergoes rapid expansion, it grows to become much larger than the observable universe. What is seen today in opposite directions on the sky would once have been neighbouring parts of a much smaller patch. The second feature is the near flatness of space. As discussed earlier, measurements of the cosmic microwave background show that the observable universe is extremely close to spatially flat. In the equations of general relativity, a flat universe is a kind of balanced case between universes with positive and negative curvature. Without a special mechanism, even small deviations from perfect flatness in the early universe would tend to grow over time, leading to strong curvature today. Inflation provides such a mechanism. Rapid, accelerated expansion stretches any initial curvature so much that within a finite region space becomes almost indistinguishable from an exactly flat geometry. A common analogy stated in simple terms is to imagine drawing a small shape on the surface of a balloon and then inflating the balloon until the local patch looks nearly flat. Inflation does something similar in 3 dimensions, driving the observable region toward flatness regardless of its initial curvature. In many inflationary models, this process is driven by a field often called the inflaton field, whose energy density remains nearly constant over a short interval. In general relativity, a nearly constant energy density that fills space has a repulsive gravitational effect. It causes the expansion of the universe to accelerate. When the field slowly changes and its energy is released into ordinary particles, and radiation inflation ends, and the more familiar hot Big Bang phase begins with expansion, continuing at a slower, decelerating, or later accelerating rate, depending on the balance of matter and dark energy. The key point is that even if inflation lasts only for a very brief duration, the amount of expansion can be enormous. In many scenarios, space grows by factors so large that a region initially much smaller than an atomic nucleus becomes large enough to encompass the entire observable universe and far beyond. This stretching explains why the cosmic microwave background looks so uniform and why space appears so flat over the scales that can be measured. It also suggests strongly that the total universe is far larger than the patch that can currently be seen. Inflation does more than smooth and flatten. Quantum mechanics implies that fields cannot be perfectly uniform. There are always small fluctuations in their value. During inflation, these quantum fluctuations in the inflaton field are stretched to cosmic scales. After inflation ends, they become tiny differences in density and temperature in the hot plasma. Over billions of years, gravity amplifies these small seeds into the large-scale structures seen today, clusters of galaxies, filaments, and voids. Measurements of the cosmic microwave background show a pattern of temperature variations whose statistical properties match those predicted by simple inflationary models. This agreement is one of the reasons inflation is widely regarded as a successful extension of the standard cosmological picture. When these pieces are put together, a particular picture emerges. The observable universe is a finite region that has grown out of a much smaller, nearly uniform patch of space that underwent rapid inflationary expansion. The flatness and homogeneity of this region are natural outcomes of that process. However, inflation itself does not need to stop at the boundary of what is now observable. In most models, the inflationary expansion acts on a much larger domain. Only a small subregion of that original domain corresponds to what can now be seen from Earth. The rest extends beyond the horizon and remains unobservable in principle. In many mathematical treatments, this larger domain is effectively infinite. Even in scenarios where the total inflating region is finite, the physical size can be vastly larger than the observable universe, so large that for all practical purposes it behaves like an unbounded expanse. Some versions of inflation go further and suggest that the process may be eternal into the future with different regions ending inflation at different times. These ideas belong more fully to the next stage of the narrative, but even without them, standard inflation already changes the way the size of the universe is understood. Under inflation, the finite age of the hot Big Bang phase does not translate directly into a limit on the size of space. Instead, it becomes the age of the post-inflationary universe, while the underlying inflating region may have been much larger and may have existed in a more complex way. Observationally, inflation is supported by indirect evidence. The pattern of temperature and polarization fluctuations in the cosmic microwave background, the distribution of galaxies on large scales, and the near flatness of space all fit comfortably within inflationary expectations. Different models of inflation make slightly different predictions, and observations help to rule out some possibilities and constrain others. Yet all of this testing takes place within the observable patch. Inflation is inferred from its footprints there. Its full spatial extent remains hidden. For the infinity question, this situation is both suggestive and incomplete. On one hand, inflation explains why the universe visible today seems to be just a small part of a much larger structure. It provides a mechanism by which a modest initial region can be stretched far beyond any horizon that can ever be reached, making it entirely natural to think of a universe that is vastly larger than the observable bubble and possibly infinite. On the other hand, the theory is still an extrapolation. It is based on physical principles tested in other contexts, but the inflationary epoch itself lies far beyond direct laboratory reach. The details of the inflaton field, its potential energy, and the precise manner in which inflation starts and ends are still matters of active research. Alternative ideas exist, and while many of them share the feature of producing a very large universe, they do so with different underlying mechanisms. In this part of the story, inflation therefore functions as a bridge between firm observations and more speculative territory. It grounds the idea of a universe that is much larger than the observable region in a concrete physical process rather than in simple imagination. It shows how a finite age and a finite horizon can coexist with a spatial extent that may be for all practical purposes without limit. At the same time, it leaves open the question of ultimate infinity, because even an inflating universe can in principle be finite if the underlying space has an appropriate topology, or if the inflationary process itself is restricted in scope. What inflation does fix to a large extent is the expectation that the observable universe is not the whole story. It suggests that the smooth, nearly flat region that can be mapped is one small part of a much greater expanse, an expanse whose full reach may never be directly known, but whose existence is written subtly into the uniform glow of the cosmic microwave background and the quiet regularity of the large-scale cosmic web. When inflation is extended from a single brief episode to a larger framework in which it can continue in different regions at different times, the picture of the universe becomes even more vast and speculative. This broader idea is often called eternal inflation. In many inflationary models, the same mechanism that drives rapid expansion also makes it difficult for inflation to end everywhere at once. Quantum fluctuations in the inflaton field cause its value to vary slightly from place to place. In some regions, the field may roll down its potential energy landscape quickly and end inflation, converting its stored energy into particles and radiation, and beginning a hot big bang phase like the one that leads to the observable universe. In other regions, fluctuations may keep the field near a high energy state for longer, so inflation continues there. Because inflation stretches space at an accelerating rate, regions that keep inflating grow faster than regions where inflation has ended. Even if the probability that inflation ends in a given patch per unit time is not extremely small, the patches in which it persists can dominate the total volume of space. The resulting picture is of a cosmos in which pockets where inflation has stopped, sometimes described as bubble universes, are embedded within a larger inflating background that never completely switches off. Each bubble is a region where the inflaton field has decayed, reheating that region, and giving rise to a hot, dense state, followed by a more ordinary expansion. Such a bubble can, in principle, grow to enormous size with internal physics that may resemble the familiar universe, or may differ depending on the details of the underlying theory. Inside each bubble, observers would see a cosmos that looks broadly like a standard expanding universe, with its own galaxies, cosmic microwave background, and large-scale structure. From their viewpoint, it would be natural to describe the history in terms of a single Big Bang followed by expansion. At the same time, in the surrounding inflating space, new bubbles could continue to form in other locations. Over long times, the overall structure becomes a complex collection of thermalized regions separated by domains where inflation still drives accelerated expansion. This is the essence of eternal inflation. It is eternal not in the sense that any given local patch inflates forever, but in the sense that somewhere inflation always continues creating new regions indefinitely into the future. In many mathematical treatments, this process yields a space-time with infinitely many bubble universes, each potentially infinite in spatial extent, and separated from others by vast inflating stretches. For the question of whether the universe is infinite, this framework changes the way the word universe is used. The observable universe becomes one bubble, one region, where inflation has ended and a hot Big Bang phase has unfolded. The term multiverse is sometimes used to refer to the entire collection of bubbles plus the inflating background. Within this larger structure, the spatial extent can be infinite, the number of bubbles can be infinite, and even the number of observable universes like the one around Earth can be without bound. Yet all of this remains beyond direct observation, inferred only from the mathematical behavior of inflationary fields and from attempts to extend those models into regimes that cannot be tested in the laboratory. Eternal inflation arises naturally in certain classes of scalar field models, where the inflaton evolves slowly, and quantum fluctuations are significant over the scales of interest. In these models, the field value in any given region undergoes a kind of random walk superimposed on its classical rolling down the potential. Some regions fluctuate upward, increasing their local energy density and prolonging inflation. Other regions fluctuate downward and exit inflation. The balance between these tendencies determines whether the overall process is eternal. In many cases, the exponential growth of volume in regions that remain inflating outpaces the rate at which new, non-inflating regions form, so the inflating domains never disappear. The resulting space-time is highly inhomogeneous on the larger scales, even though each bubble can be internally homogeneous and isotropic to a very good approximation. Observationally, eternal inflation is extremely difficult to probe. If bubble universes are separated by regions of inflating space with very high energy density, the boundaries between them are expected to be hostile environments with large gradients and possibly violent events when bubbles collide. The interior of one bubble is effectively causally disconnected from the interiors of most others, because the intervening inflating space stretches distances so rapidly that signals cannot cross. In principle, a collision between the bubble containing the observable universe and another bubble in the early stages of its history could leave a faint imprint on the cosmic microwave background, such as a subtle disk-like feature with slightly different statistical properties. Some studies have searched for such signatures, but no convincing evidence has been found so far. The absence of clear bubble collision signals does not disprove eternal inflation, because collisions might be rare or might leave imprints too subtle for current instruments to detect. Eternal inflation also raises conceptual challenges. An infinite or extremely large ensemble of bubble universes complicates the question of how to define probabilities. If there are infinitely many regions with different properties, and if each type of region is realized infinitely many times, it becomes non-trivial to say how likely it is to find oneself in any particular type. This difficulty is often referred to as the measure problem in eternal inflation. Different ways of regulating or truncating the infinite space-time lead to different answers, and there is currently no consensus on which approach, if any, is correct. Despite these issues, eternal inflation is widely studied because it arises as a generic behavior in simple field theories, and because it offers a bridge to broader ideas in high-energy physics, including scenarios in which different bubbles realize different effective laws of physics. For the narrative about infinity, eternal inflation contributes a specific kind of speculation. It does not just suggest that the universe might be larger than the observable region. It suggests that reality as a whole might contain an unending variety of regions, each with its own cosmic evolution, and that the observable universe is one example among countless others. In such a picture, asking whether the universe is infinite can be interpreted in several ways. The spatial extent inside a single bubble might be infinite or finite depending on its internal curvature and topology. The collection of bubbles might be infinite in number. The total inflating background might be infinite in volume. The answers to these questions depend on details of the theory that are not yet known. From a more cautious standpoint, it is possible to step back and note what eternal inflation changes and what it leaves untouched. It changes the expectation that the hot Big Bang is a unique global event. Instead, it becomes a local episode in a larger multi-stage structure. It changes the way the observable universe is regarded, recasting it as a region within a broader inflating environment. It reinforces the idea that the finite horizon around Earth samples only a small part of a much more extensive reality. At the same time, it does not yet provide directly testable predictions that distinguish it sharply from simpler non-eternal inflationary scenarios at the level of current measurements. The cosmic microwave background and large-scale structure can be explained by both kinds of models, and the extra structure introduced by eternal inflation lies mostly beyond observational reach. In this part of the story, eternal inflation therefore serves as an example of how modern cosmology pushes the infinity question into new domains. It takes the already large universe suggested by ordinary inflation and extends it into a framework where the total structure may be effectively unbounded in both space and the number of distinct regions. It shows how a finite observable universe can be embedded in a possibly infinite multiverse. Yet it also illustrates the limits of current knowledge, because the mechanisms that drive eternal inflation operate at energies and scales far removed from direct experiment. The idea remains a powerful mathematically motivated way to imagine an infinite cosmos, but whether nature has chosen this particular route to infinity is something that present data cannot confirm or exclude. The ingredients that fill the universe play a decisive role in how space behaves over time and in how the question of infinity is framed. Among these ingredients, dark matter and dark energy are especially important. Ordinary matter, the kind that forms stars, planets, gas and dust, accounts for only a small fraction of the total cosmic energy budget. Observations of galaxy rotation curves, motions within clusters, gravitational lensing, and the pattern of temperature fluctuations in the cosmic microwave background all indicate that there is additional mass-present mass that does not emit or absorb light in any detectable way. This unseen component is called dark matter. It interacts gravitationally, helping to bind galaxies together and to shape the growth of large-scale structure, but it does not interact with electromagnetic radiation in the same way as ordinary matter. In addition to dark matter, there is evidence for a more mysterious component, dark energy, which seems to drive the accelerated expansion of the universe. Measurements of very distant supernovae, combined with data from the cosmic microwave background and galaxy surveys, show that the expansion rate of the universe is not slowing down under gravity alone. Instead, over the last several billion years, the expansion has begun to accelerate. In the framework of general relativity, this behavior can be described by adding a term to the equations that acts like a uniform energy density filling space with negative pressure. The simplest version of this term is the cosmological constant. More general versions involve a slowly varying field. Whatever its detailed nature, dark energy acts in opposition to gravity on large scales, pushing galaxies apart and increasing the rate at which space expands. The balance between ordinary matter, and dark energy determines not only the current expansion rate, but also the ultimate fate of the universe. In a cosmos filled only with matter and radiation, gravity would slow the expansion. Depending on the total density and curvature, the universe could either expand forever at an ever-decreasing rate, or eventually halt and recollapse. The presence of dark energy changes this picture. If dark energy behaves like a cosmological constant, its energy density remains roughly constant as space expands, while the density of matter and radiation decreases as they are spread over larger volumes. Over time, dark energy comes to dominate the dynamics. Once this domination begins, the expansion tends toward a phase of accelerated growth. Distances between galaxy clusters increase more and more rapidly. Nearby galaxies bound together by their mutual gravity remain connected, but unbound structures recede beyond each other's reach. From the perspective of an observer within a typical galaxy, the distant universe grows dimmer as more galaxies cross a kind of event horizon defined by the accelerated expansion. Light emitted now from regions beyond this horizon will never arrive. Even if space is spatially infinite, the portion that can ever send signals to a given world line becomes limited. The observable universe in this sense approaches a finite volume that contains only the structures that remain gravitationally linked. For the infinity question, this has a subtle implication. Dark energy can produce a situation in which space is infinite, but the part of that space that can ever be observed or influenced from any given location is finite. As time goes on, more and more of the infinite expanse becomes causally disconnected. The physical reality of regions beyond the event horizon remains part of the global solution of the equations, but they are forever beyond contact from a given vantage point. In contrast, if the universe contained enough matter to eventually halt expansion and reverse it, the long-term picture would be different. In such a closed, recollapsing universe, the expansion would slow stop and turn into contraction. Over very long times, galaxies and clusters would draw closer, and the entire observable region would head toward a final hot, dense state, sometimes called a big crunch. In such a scenario, the total lifetime of the universe would be finite in time, although the spatial extent at maximum expansion could still be very large and possibly infinite in certain models. The dark energy component, as currently inferred from observations, however, favours a future in which accelerated expansion continues indefinitely, at least in the simplest cosmological constant case. There are more exotic possibilities. Some models allow dark energy to vary with time. If its density decreases in the far future, the acceleration could slow, perhaps even giving way to a different phase of evolution. Other models allow dark energy to increase in strength, leading to scenarios in which the expansion becomes so rapid that even bound structures are eventually torn apart in a so-called Big Rip. These scenarios remain speculative and depend sensitively on the detailed behavior of dark energy, which is still poorly understood. Current data indicate that dark energy behaves in a way very close to a cosmological constant, but small deviations cannot yet be ruled out. In all these cases, the fate of the universe is closely linked to the content of dark matter and dark energy, but the question of spatial infinity remains only partly constrained. An eternally expanding universe driven by dark energy can be spatially infinite or finite. If it is infinite, the total volume continues to grow without bound, and the number of galaxies and stars may be infinite, even though the number accessible from any one galaxy remains limited. If it is finite but unbounded, the overall volume can still grow arbitrarily large as the scale factor increases, even though the topology enforces a closed structure. In that case, infinity may appear not in spatial extent but in the unending progression of time and the continuous dilution of matter and radiation. Dark matter plays a quieter but essential part in this story. Its presence enhances the growth of structure in the early universe, allowing small fluctuations in density to grow into the cosmic web mapped by surveys. Without dark matter, the universe would be smoother on large scales, and the distribution of galaxies would differ significantly from what is observed. The amount of dark matter compared to dark energy also enters into the equations that describe the expansion history. By measuring galaxy clustering gravitational lensing and the cosmic microwave background, cosmologists estimate the relative contributions of ordinary matter, dark matter, and dark energy. These estimates feed back into models of the universe's past and future. The more precise they become, the more tightly they constrain which broad classes of cosmological scenarios are viable. Yet even with these constraints, the deepest questions remain open. Knowing that dark energy drives accelerated expansion, and that dark matter shapes the growth of structure, tells a great deal about the evolution of the observable universe. It does not by itself determine whether space is infinite or finite, whether time extends without end, or whether the fundamental topology allows paths that eventually return to their origin. What it does provide is a clearer sense of how different infinity scenarios would unfold. In a universe with eternal acceleration and infinite space, most of the cosmos becomes permanently inaccessible, with island galaxies adrift in an ever-thinning sea of dark energy. In a universe with a finite volume and eternal expansion, the total stage remains limited but stretches, and the same isolation occurs as horizons shrink in comoving terms. In a universe that recollapses, time becomes finite, but the structures within the finite space can explore more of each other's volume before the final contraction. In this part of the narrative, dark matter and dark energy thus act as subtle guides. They shape the large-scale structure, set the pace of expansion, and define event horizons. They do not answer the infinity question directly, but they narrow the range of plausible cosmic futures and show how different answers to that question would be experienced by any observers bound to particular galaxies. The present evidence points toward a universe in which dark energy continues to dominate, leading to accelerated expansion that persists for an immense duration. Whether this evolving stage is infinite or finite in its full extent remains unknown, but its dynamics ensure that from any single point of view, only a finite part can ever be seen, even if beyond that region space and time continue without end. The idea of a cosmic horizon comes from combining the finite age of the universe with the finite speed at which information travels. Like gravitational waves and any signal limited by relativity, cannot move faster than a fixed speed through space. At the same time, space itself expands, carrying galaxies away from each other. The interplay between these effects produces boundaries that mark how far influence can reach and how much of the universe can ever be seen from any given place. These boundaries are not made of matter. They are not physical shells that something could touch. They are limits in space-time defined by which events can send signals that arrive and which events remain forever disconnected. One important concept is the particle horizon. This is the maximum distance from which light could have travelled to an observer since the hot dense phase began. It marks the edge of the observable universe at a given time. Inside this radius, light from early events has had time to arrive, building the images and maps that form modern cosmology. Beyond this distance, even if galaxies and structures exist, their light has not yet completed the journey, and so they remain unseen. The particle horizon grows as time passes because light from ever more distant regions has more time to reach the observer. In that sense, the observable universe slowly enlarges. Another more subtle concept is the event horizon. While the particle horizon tells how far past events can have influenced an observer, by the present time the event horizon tells which events will ever be able to influence that observer in the future. In an expanding universe with dark energy that drives accelerated expansion, the event horizon defines a maximum co-moving distance from which signals emitted now can ever arrive, even given infinite time. Galaxies beyond this event horizon recede in such a way that light emitted from them at the present epoch will never catch up. They disappear not because they move through space faster than light, but because the space between them and the observer stretches so quickly that the distance to be crossed grows too fast. The distinction between these horizons is important. The particle horizon grows with time, revealing new regions as light that has been travelling for billions of years finally arrives. The event horizon in a universe dominated by dark energy can remain at a finite moving distance and act as a permanent limit on what can ever be seen in principle. A distant galaxy might be inside the particle horizon today so that its ancient light is visible, and yet already beyond the event horizon so that any light it emits now will not be observed in the far future. This layered structure shows that the phrase observable universe has a time-dependent meaning. The region that has been able to send signals so far is not the same as the region that will always remain in communication. Both regions are smaller than the total space described by cosmological models, which may stretch far beyond either horizon. For the infinity question, these horizons carry a clear message. The fact that only a finite portion of the universe can ever be observed from a given location does not tell whether the total universe is finite or infinite. Even in a spatially infinite cosmos, each observer has a particle horizon, and in many models an event horizon as well. The global picture may contain endlessly many galaxies and structures, but any single world line samples only a limited subset. In a spatially finite universe with a very large volume, the horizons may sit well inside the full extent, so that not even a complete tour of all possible times would reveal the entire structure from one vantage point. Horizons therefore mark limits of information rather than limits of existence. They also emphasize how local cosmology really is. The maps of galaxies, the measurements of the cosmic microwave background, and the surveys of large-scale structure all describe only the region inside the current particle horizon. When cosmologists speak of the universe beyond that region, they're making an inference based on symmetry and on the success of models that assume homogeneity and isotropy. The assumption is that the same physical laws and the same broad statistical properties apply outside the observable volume as inside it. This assumption is supported by the uniformity observed across the entire visible sky. There is no sign that one direction is special or that conditions change drastically as the horizon is approached. The cosmic microwave background has nearly the same average temperature in every direction. Galaxy surveys show similar clustering statistics in widely separated regions. These facts encourage the extension of the standard cosmological model beyond the observable sphere, but they do not compel it. Nature could in principle depart from this pattern beyond the limits of current observation. Another feature of horizons is that they are not anchored to any absolute center. In a universe that is homogeneous and isotropic on large scales, every observer, wherever that observer might be, sits at the center of a personal observable universe defined by the same rules. Each world line has its own particle horizon, and in models with accelerated expansion, its own event horizon. The view from any one galaxy is therefore one example among many. The same volume that is currently observable from Earth is merely a different shell around a different center for observers in distant galaxies. The existence of horizons does not select a special place in space. It secures the idea that the limits of observation are always local, and that they arise from the shared history of expansion and the finite speed of light. This perspective helps clarify what is meant by speaking of regions beyond the observable universe. Those regions are defined not by a physical boundary, but by a lack of causal contact. No signal from there has arrived yet, and some signals will never arrive, but this lack of contact is symmetric. Regions beyond the horizon are just as cut off from the observable patch as the observable patch is from them. In a spatially infinite universe, such disjoint regions can be endlessly many. Each contains its own observable sphere bounded by its own horizons with its own maps and data. In a very large but finite universe, horizons still partition space-time into volumes that cannot fully exchange information within the available time. The interplay between horizons and expansion also shapes how the night sky will evolve. As dark energy continues to drive accelerated expansion, more galaxies cross the event horizon and fade from view. The observable universe in the sense of the region that can ever send new light shrinks in comoving terms. Any given observer may eventually find that only the local group of gravitationally bound galaxies remains visible. In that distant future, the cosmic microwave background will have redshifted to such long wavelengths that it becomes effectively undetectable, and the evidence for the hot Big Bang will be harder to reconstruct. From within that future island of matter, the inference that the universe was once filled with distant galaxies and that space might be infinite will rest entirely on the records preserved from earlier eras. In this part of the narrative, horizons show how the finite and the infinite coexist in cosmology. They demonstrate that even if space has no bound, there are strict limits on what can be known from any point. They also show that the absence of a visible edge in current maps does not guarantee an infinite universe, because those maps cannot reach beyond the particle horizon. At the same time, the presence of horizons is fully compatible with a truly infinite cosmos, one in which an unending collection of regions lies forever beyond reach. The horizons themselves are therefore best understood as dynamic frontiers of information. They expand, recede, and change character as the universe evolves, but they do not by themselves settle the question of whether the cosmic expanse they carve into reachable and unreachable zones is ultimately finite or without end. They simply mark at each moment how far the story has been read while leaving the length of the book unknown. On the very largest scales that can be mapped, the matter in the universe arranges itself into a pattern that is often called the cosmic web. This structure emerges from galaxy surveys that measure positions and distances for millions of galaxies across large portions of the sky. Each galaxy sits at a point in three-dimensional space, and when these points are plotted together, they reveal that galaxies do not fill space evenly like grains of sand. Instead, they gather along filaments, sheets, and nodes, with vast low-density regions or voids in between. Clusters of galaxies occupy the densest nodes where several filaments meet. Superclusters extend along arcs and walls that can span hundreds of millions of light-years. The voids between them can be almost as large. As the survey volume grows, more of this pattern appears great chains of clusters stretching across space, enormous underdense bubbles and complex networks that at first glance might seem to continue without end. These maps are not static pictures. They are snapshots of a dynamic process shaped by gravity acting over billions of years. Small initial fluctuations in density seeded in the early universe and recorded in the cosmic microwave background grow under the pull of dark matter. Regions that are slightly denser than average attract more matter, becoming denser still, while less dense regions lose material and become more empty. Over time, this amplifies contrast and transforms a nearly uniform matter distribution into the web of structures observed today. Numerical simulations of structure formation, which follow the evolution of dark matter and gas under gravity and cosmic expansion, reproduce this web when they start from initial conditions consistent with observations. The agreement between simulations and surveys supports the idea that the cosmic web is an expected outcome of known physics, applied to a universe with the measured contents of ordinary matter, dark matter, and dark energy. Even so, certain features of the larger structures raise natural questions. Surveys have discovered enormous walls and filaments with lengths of several 100 million light-years. Some analyses have claimed evidence for structures on even larger scales, though such claims are often debated because they approach or exceed the scales, where the assumption of statistical uniformity is expected to hold. There is a scale beyond which, in the standard cosmological model, the universe should appear homogeneous when averaged over large enough volumes. On scales smaller than this, clustering produces strong variations in density. On scales larger than this, those variations should average out, and the universe should look almost the same everywhere. Determining this homogeneity scale in practice requires surveying very large volumes and counting galaxies over long distances. Results so far suggest that when averaged over scales of a few 100 million light-years and above the matter, distribution does approach uniformity. The cosmic web with all its filaments and voids then appears as a pattern superimposed on an underlying homogeneous background. This supports the use of simple cosmological models that treat the universe as smooth on the largest scales. At the same time, the presence of such large coherent structures invites speculation about whether the web has a characteristic maximum size, or whether similar patterns continue on scales beyond the current survey limits. If the universe is spatially infinite and statistically homogeneous, then the cosmic web does not have a final outer boundary. Instead, structures of all sizes up to some maximum determined by the growth history are expected to recur throughout space. The largest filaments and voids seen in present surveys would be examples drawn from a distribution that in principle continues across an unbounded volume. If the universe is finite but very large, the web could still fill it completely, wrapping around in ways determined by the topology. In that case, travelling or looking far enough could in principle reveal repetitions of large patterns as light circles the cosmos, although as earlier sections have noted, current searches have not found clear evidence for such repetition on observable scales. The cosmic web also feeds back into the infinity question through the concept of cosmic variance. Because only one observable universe exists from any given vantage point, and because only a finite volume can be surveyed, the statistics of the larger structures are limited by the fact that only one realization of the underlying random process is available. On small scales, there are many independent regions to sample, and averages converge quickly. On scales comparable to the survey volume, there are only a few independent patches, and random fluctuations can be large. This means that the exact arrangement of filaments and voids seen in the observable universe might not be typical of the full cosmos, especially if that cosmos is infinite. Some regions elsewhere could contain somewhat larger or smaller structures, denser clusters, or emptier voids. The maps available today therefore offer a detailed view of one finite portion of the cosmic web, but they do not uniquely determine how that web behaves on arbitrarily large scales. Simulations help fill this gap by evolving many different realizations of the same statistical model and examining the range of possible patterns. They show that within the standard cosmological framework, very large walls and filaments are rare but not impossible outcomes. This reduces the need to invoke exotic physics to explain them, and suggests that the observed web can be understood as one instance of a general pattern. Still, the presence of very large structures reinforces the idea that the universe is at minimum vast enough to allow such patterns to form naturally. Whether the pattern repeats endlessly or eventually runs out remains unknown. Another layer of information comes from how the cosmic web appears at different times. Deep surveys can observe galaxies at a range of redshifts which correspond to different look-back times. At higher redshifts nearer to the hot Big Bang phase, the web appears less developed. Clusters are smaller, and less relaxed filaments are fainter, and voids are less empty. As cosmic time progresses, gravity amplifies contrasts and the web sharpens. Tracking this evolution helps confirm the role of dark matter and the influence of dark energy on the growth of structure. It also shows that the web is not a fixed pattern, but a dynamic, ongoing process that will continue into the future as long as gravity can draw matter together against the pull of expansion on the scales where it remains effective. Looking at the cosmic web from the perspective of infinity, one can say that it provides a clear example of how a finite observable structure can hint at a larger whole without fully revealing it. The web that is mapped today extends to the edges of existing surveys, and its features remain rich and complex up to those limits. There is no visual sign in the data that the pattern is about to stop. Filaments and voids continue as far as instruments can trace them, matching expectations for a universe that is at least much larger than the observed volume. If space is infinite, this continuation extends without end. If space is finite but very large, the pattern may eventually wrap around in ways that are currently undetectable. In either case, the maps of large-scale structure are consistent with a cosmos that on the scales probed so far has no obvious boundary. In this part of the narrative, the cosmic web therefore acts as a concrete image of the universe on its largest known scales. It shows how gravity and expansion work together to shape matter into a network that fills the observable volume. It confirms that the simple homogeneous cosmological models are good descriptions when averaged over sufficiently large distances, even though the local distribution is highly structured. And it suggests through its apparent continuation up to the survey edge that the region mapped so far is likely only a fragment of a much larger arrangement. The web does not answer whether that larger arrangement is infinite, but it gives a detailed view of how an apparently endless pattern can arise from well-understood physics, operating within a finite observable domain. In this sense, large-scale structure stands as another stepping stone in the exploration of cosmic infinity, linking precise measurements to the enduring question of how far the universe goes beyond the furthest filaments currently seen. Cosmology as practiced from a planet around an ordinary star faces an unavoidable limitation. All data come from a single vantage point in a single observable volume. The standard models assume that on very large scales the universe is statistically homogeneous, an isotropic meaning that its properties averaged over enormous regions do not depend on location or direction. This assumption, often called the cosmological principle, is supported by many observations within the observable universe. The cosmic microwave background has nearly the same temperature in every direction, with only tiny fluctuations. Galaxy surveys show similar clustering statistics in widely separated parts of the sky. Yet the fact remains that these tests are carried out in only one realization of the universe, not over an ensemble of different universes. The consequence of this is known as cosmic variance. Cosmic variance describes the fundamental uncertainty that arises because only a finite sample of the universe can ever be observed. Even if the underlying statistical laws are perfectly known, the specific pattern seen in one observable volume is only one possible outcome. Just as rolling a die many times produces a distribution of results that fluctuates around the ideal average, the distribution of matter and radiation in the observable universe fluctuates around its theoretical mean. On small scales, many independent regions can be sampled so the averages converge closely to the expected values. On the largest scales, the number of independent regions is small, and deviations from the average can be significant. In practice, this means that certain quantities such as the amplitude of cosmic microwave background fluctuations on the very largest angular scales, or the number of extremely large structures like giant walls and voids cannot be determined with arbitrary precision. The uncertainty is not due to measurement error or instrumental noise. It is built into the nature of observing only one sky. As a result, cosmologists quote cosmic variance limits when stating how well some properties of the universe can ever be known. These limits remain even as instruments improve because no new telescope can provide more than one sky worth of data from a single vantage point. For the question of whether the universe is infinite cosmic variance has a subtle but important impact. Many of the key arguments for or against infinity rely on extrapolating from observed uniformity. The fact that the cosmic microwave background looks the same in all directions on large scales suggests that the observable universe is a fair sample of a much larger whole. The measured near flatness of space hints that the universe is either extremely large or infinite. The homogeneous appearance of the cosmic web on the largest surveyed scales supports the use of simple models that extend beyond the horizon. However, all these inferences assume that the observed region is not a rare outlier. Cosmic variance reminds that there is always some probability, however small, that the observable volume is not entirely typical. It could in principle sit in a region where fluctuations on large scales happen to produce slightly unusual values compared to the global average. For most practical purposes, cosmologists treat the observable universe as representative, because doing so leads to a coherent model that successfully explains a wide range of data. The deviations allowed by cosmic variance are usually small compared to the overall patterns. Yet when questions about infinity are posed, these small uncertainties gain weight. If the total universe is spatially infinite and statistically homogeneous, then the observable region is one of infinitely many similar regions, each with its own realization of the same underlying random process. Some will have slightly higher densities on the larger scale, some slightly lower. Some will contain particularly large structures or slightly unusual alignments. The observed universe would then be a typical realization in a vast ensemble. The fact that it exhibits near flatness and large-scale uniformity would be understood as a reflection of the underlying laws that apply everywhere. If the total universe is finite with a volume only modestly larger than the observable region, then the observable volume might capture a large fraction of all that exists. In that case, any deviations from homogeneity caused by cosmic variance would be more directly linked to global properties. The pattern of large-scale structure might tell more about the finite whole. However, unless clear signatures of finiteness such as repeating patterns or matched circles are detected, the data from a single region will still be compatible with both finite and infinite scenarios within the allowed range of cosmic variance. Cosmic variance also influences how anomalies are interpreted. In maps of the cosmic microwave background, certain features on the largest angular scales, such as alignments of low-order multipoles or slightly lower power than expected, in some modes have been noted and discussed. Some researchers have explored whether these features point to new physics or to departures from simple cosmological models. Others have argued that given the limitations of cosmic variance, such anomalies may simply be statistical fluctuations in a single realization and do not necessarily require any change in the underlying model. The debate illustrates how difficult it is to use the larger scale data to draw firm conclusions about global properties of the universe. For the infinity question, the existence of such anomalies neither proves nor disproves an infinite cosmos. It simply shows that the observable universe may have quirks that must be weighed against the expectations of statistical models. Another aspect of the single vantage point is that all observations are made from a location associated with a particular galaxy cluster and cosmic environment. In principle, if it were possible to travel to a distant galaxy and observe from there the pattern of nearby structures, and the detailed view of the cosmic microwave background would differ. The dipole anisotropy caused by motion, the distribution of nearby clusters, and the local flow of matter toward large structures would change. However, on sufficiently large scales, the statistical properties would remain the same if the cosmological principle holds. The fact that the view from Earth appears consistent with large-scale isotropy is therefore taken as evidence that the universe does not single out a special place. Yet this conclusion too rests on the assumption that the observable volume around Earth is typical. Cosmic variance places a theoretical limit on how confidently that assumption can be upheld even as data continue to support it. The presence of cosmic variance does not undermine the overall success of cosmology. Instead, it defines a horizon for knowledge that is conceptually similar to the horizons imposed by light travel time and expansion. Just as there are regions of space that cannot be seen because their light has not arrived or will never arrive, there are aspects of the universe's global properties that cannot be pinned down beyond a certain precision because only one sample is available. These epistemic horizons do not mean that cosmology is purely speculative. They mean that some questions, especially those that ask about ultimate size, exact global curvature, or the full extent of structure beyond the observable volume, may never receive definitive numerical answers. Instead, they will be addressed in terms of plausible models that fit the data and in terms of ranges within which key parameters can lie. In this part of the narrative, cosmic variance and the single vantage point highlight why the infinity question remains open, even when the local universe is well described by precise measurements and successful theories. The observable universe provides a rich, detailed picture of how matter and radiation behave on scales from galaxies to the cosmic web. It constrains models of curvature topology, dark matter, dark energy, and inflation. Yet the fact that all of this information comes from one finite region ensures that arguments about infinity must always contain an element of extrapolation. The best that can be said with confidence is that within the observable horizon, the universe behaves as if it were part of a much larger, nearly homogeneous structure. Whether that structure continues without end, closes upon itself in a subtle topology, or forms part of an even more complex multiverse remains beyond the reach of direct demonstration. Cosmic variance stands as a reminder that some aspects of the cosmos may always be known only through informed inference, not through complete observation, and that the question of infinity belongs to this class of enduring uncertainties. The usual story of the universe begins with the hot Big Bang, a phase in which matter and radiation are extremely dense, and hot space is much more compressed than it is today, and the entire observable universe fits into a much smaller volume. This phase is well supported by multiple lines of evidence. The expansion of space measured through galaxy redshifts, the existence and properties of the cosmic microwave background, and the abundances of light elements such as hydrogen, helium, and lithium, all point back to an early state in which the universe was hotter and denser than at any later time. In this sense, the hot Big Bang is not just a theoretical idea, but a description of a real extended period in the history of the observable universe. However, when the timeline is traced further back toward higher densities and temperatures, the standard equations of general relativity become unreliable. At extremely small scales and extremely high energies, quantum effects and gravity are expected to become important, and no complete theory of quantum gravity has yet been confirmed. As a result, the description of the universe as a smooth classical space-time with well-defined curvature breaks down if extrapolated too far into the past. This breakdown leaves open the question of whether the hot Big Bang is the absolute beginning of the universe, or whether it marks a transition from an earlier phase. Classical general relativity under certain conditions predicts singularities points where densities and curvatures become formally infinite, and the equations cease to make sense. The simplest Big Bang model contains such a singularity at a finite time in the past. This has often been interpreted as a sign that the universe began in a single instant of zero size and infinite density. Yet many physicists view singularities not as real physical states, but as signals that the theory being used is incomplete. Just as the description of matter as a continuous fluid fails at the scale of individual atoms, the description of space-time as a smooth manifold may fail at scales where quantum gravity is important. Various theoretical approaches explore what might replace the classical singularity. Some models propose that the universe underwent a bounce contracting from a larger size down to a minimum volume before re-expanding into the hot Big Bang phase. In such scenarios, cosmic time could extend further into the past than the hot Big Bang, and there might have been a previous long epoch of expansion and contraction. Other models consider cyclic universes in which expansion, collapse, and bounce repeat many times. In those cases, the universe as a whole might have no beginning in a simple sense, although questions about the stability and the origin of the cycles remain. Different proposals arise from different candidate theories of quantum gravity, such as loop quantum cosmology, or certain string-inspired constructions. Another class of ideas, including some versions of inflation, treat the hot Big Bang as a local event within a larger, possibly eternal framework. As discussed earlier in eternal inflation, the hot phase that leads to an observable universe like the present one can occur in many regions at different times. In that picture, the Big Bang is not the start of everything. It is a transition within one bubble universe. The inflating background may have existed for an arbitrarily long time before that transition, and may continue indefinitely into the future. The total space-time could then be past eternal, or at least much older than the hot Big Bang in any given region, though even here there are theorems that suggest limits on how far back inflation alone can be extended. Still other approaches such as conformal cyclic models suggest that the far future of one cosmological phase can be reinterpreted as the beginning of another, smoothing the concept of a starting point. There are also proposals in which the universe emerges from a quantum state, without a classical notion of time before a certain epoch, so that asking what happened before the Big Bang has no clear meaning. In these pictures, time itself, as understood in ordinary terms, is a derived concept that becomes well defined only after the universe has expanded and cooled enough for familiar physical processes to occur. What these diverse ideas share is the recognition that the hot Big Bang, while a robust part of the observable history, may not be the ultimate origin of the universe. They differ in how they treat the very early regime, and in what they imply about whether time and space extend infinitely into the past. Some models allow an infinite past with no initial moment at which the universe begins from nothing. Others still contain a beginning in some form, perhaps smoothed by quantum effects that remove the singularity, but leave only a finite stretch of time before the hot phase. Observationally, the situation is constrained but not resolved. Data from the cosmic microwave background, large-scale structure, and element abundances tightly fix the conditions in the universe from a very early time onward. They support a hot dense origin, and are compatible with a period of inflation. They do not, however, directly reveal what happened before the earliest epoch that can be probed. Subtle signatures of a bounce, a pre-Big Bang phase, or a previous cycle might exist in the pattern of primordial fluctuations, but so far no clear unique imprint has been identified that demands one particular extension of the standard model. Many different early history scenarios can be adjusted to match the same set of late-time observations. For the question of infinity, the possibility of a pre-Big Bang or eternal framework introduces the idea of temporal infinity alongside spatial infinity. If time extends without bound into the past, the universe could be eternal in duration, even if its spatial extent is finite or extremely large but not infinite. Conversely, the universe could have a finite age but be spatially infinite, or both space and time could be infinite with no beginning and no end. The combination of possibilities is broad. What current physics provides are constraints rather than complete answers. It shows that from some early time onward, the observable universe has evolved in a way that is consistent with known laws. It suggests mechanisms such as inflation, or quantum bounces that can connect that early phase to a wider context. It also shows that purely classical notions of a sharp beginning may not apply at the highest energies, yet it stops short of proving that the universe has an infinite past or that it emerged from a true beginning in time. In this part of the narrative, the hot Big Bang is therefore reframed. Instead of being described as an absolute origin, it becomes the earliest reliably described chapter in a longer story whose opening pages are missing or blurred. theories of what comes before offer different ways to fill in those missing pages, each with implications for whether the universe is temporally finite or infinite. At present, none of these theories can claim definitive empirical support over the others. The only firm statement is that the hot Big Bang, while central to our understanding of cosmic history, need not be the first moment of existence. It is a threshold beyond which current models cannot yet see clearly. Whether beyond that threshold the universe stretches back through an infinite sequence of earlier states, arises from a finite precursor, or emerges in a way that makes the notion of before lose its usual meaning, remains one of the deepest open questions closely connected to the broader issue of whether the cosmos is infinite in any sense at all. Ideas about a multiverse arise when the known laws of physics are extended into regimes where they allow or even seem to favour more than one kind of cosmic region. In the simplest cosmological models, the word universe refers to the totality of space-time matter and energy. There is one set of laws, one connected space-time and one history. When inflation quantum mechanics and high-energy theories beyond the standard model are considered together, the picture can become more varied. In many of these extended frameworks, reality may consist of many domains, each with its own realization of physical conditions. The observable universe would then be one domain within a multiverse. This shift in viewpoint changes how questions of infinity are framed, because infinity could apply not only to the size of space within one domain, but also to the number and variety of domains themselves. Eternal inflation described earlier already provides one example. In that scenario, inflating space never ends everywhere at once. Instead, it produces a collection of bubble universes, each with its own hot Big Bang phase. From the inside, a bubble can look like a standard expanding universe, with galaxies, cosmic microwave background, and large-scale structure. From a larger perspective, it is one region, among many separated from its neighbours by stretches of still inflating space. If inflation is eternal into the future, the number of such bubbles can grow without limit. If the underlying inflating space is itself infinite, there may be an infinite number of bubble universes, each potentially very large, or even infinite internally. In this context, asking whether the universe is infinite becomes ambiguous. The spatial extent inside a single bubble might be finite or infinite depending on its curvature and topology. At the same time, the whole multiverse could contain infinitely many bubbles. Infinity may arise in more than one way at once. Another line of thought comes from quantum mechanics. In the standard formulation of quantum theory, physical systems are described by wave functions that encode many possible outcomes at once. When measurements are made, only one outcome is observed. In some interpretations, such as the many worlds, picture the wave function never truly collapses. Instead, it evolves smoothly, and the apparent collapse is understood as a branching of reality into different non-communicating sectors, each corresponding to a different outcome. Applied to cosmology, this suggests that all possible sequences of quantum events compatible with the laws of physics are realized in some branch of a larger quantum state. Each branch could correspond to a different cosmic history, perhaps even a different effective universe. In this view, the word multiverse refers not to separate regions in space, but to separate branches in a vast quantum state. The number of such branches for any long and complex history could be enormous, possibly uncountable. Infinity here is a feature of quantum possibilities rather than of spatial extent. High-energy theories that seek to unify gravity with other forces sometimes add further layers. In certain string-inspired models, for instance, there can be many different ways to compactify extra spatial dimensions and many different stable configurations of fields. Each configuration can lead to a different set of low-energy physical laws with different values of fundamental constants and different particle spectra. The collection of all such configurations is sometimes called a landscape. If eternal inflation or a similar process populates this landscape, different bubble universes could realize different effective laws of physics. Some might have physical constants that allow long-lived stars and complex chemistry, others might not. From within one such bubble the laws would appear unique and fixed, but in the larger multiverse they would be one choice among many. Here again the notion of infinity becomes layered. There could be infinitely many regions, each with its own effective physics spread across an inflating background. Some proposals also consider higher dimensional constructions, in which the observable universe is a three-dimensional surface or brane, embedded in a higher dimensional space. Other branes with their own matter and forces could exist parallel to it, separated by distances in the extra dimensions. Collisions or interactions between branes might produce events that resemble Big Bangs. In such models, the larger structure can host many branes, each with its own internal universe. Whether the number of branes is finite or infinite depends on details of the theory, but in many cases the mathematical framework allows indefinitely many such objects. For a calm and careful narrative about infinity, it is important to distinguish what is firmly established from what is speculative. The existence of multiple observable universes, each with potentially different laws, is not something that current observations can confirm. The multiverse scenarios described above are motivated by attempts to solve theoretical puzzles, such as the fine-tuning of certain constants, the behavior of inflationary fields, or the unification of forces. They are consistent with known physics in some regimes, and provide frameworks within which infinity can be naturally realized. However, they also depend on assumptions about physics at energies far beyond direct experimental reach. At present they remain proposals rather than established descriptions of nature. Observational access to other domains, if they exist, appears very limited. Bubble universes born in eternal inflation are typically separated by regions of high energy, inflating space that expand too fast to allow communication. Quantum branches in a many worlds picture do not interact in ways that would allow information to pass between them. Branes in higher dimensional spaces may be separated by distances that cannot be traversed by ordinary matter or radiation. Occasional suggestions have been made that certain subtle imprints, such as traces of bubble collisions in the cosmic microwave background, or particular statistical patterns in primordial fluctuations, might provide indirect evidence for a multiverse. So far, no clear and widely accepted signature has been found. The observable universe continues to look like a single coherent region governed by one set of physical laws. From the perspective of the infinity question, the multiverse concept does not resolve whether the observable universe itself is infinite in space. Instead, it extends the question into new territory. Even if the observable universe were shown to be spatially finite, the totality of all domains in a multiverse could still be infinite. Conversely, even if space within the observable universe is infinite, the number of distinct sets of physical laws realized across the multiverse might be finite, determined by the structure of the underlying theory. Infinity might apply to some aspects of the whole and not others. The multiverse picture also changes how rarity is understood. In an infinite or extremely large multiverse, regions with very unusual properties can exist somewhere, even if they are extremely unlikely when measured against the typical behavior of the theory. This leads to discussions about selection effects in which observers arise only in regions whose properties allow complex structures. Such arguments are sometimes used to explain why certain constants appear finely tuned for the existence of long-lived stars or stable atoms. However, these ideas depend heavily on how probabilities are defined across an infinite ensemble, a problem that is not yet resolved. In a calm summary, one can say that multiverse scenarios offer many ways in which the word infinite can enter cosmology. There can be infinite space within one domain, infinitely many domains, infinite sequences of quantum branches, or infinitely many realizations of different effective laws. Each scenario arises from extending well-tested physical principles into regimes where direct evidence is scarce. Each provides a possible context in which the observable universe is one part of a larger structure, yet none of them is required by the data gathered so far. The universe that is seen with its nearly flat geometry, its cosmic microwave background, its dark matter and dark energy, and its evolving web of galaxies can be described without invoking other domains. Multiverse ideas remain carefully framed possibilities that illustrate how deeply the notion of infinity can be woven into physics if nature has chosen those paths. In this part of the narrative, the goal is not to endorse one particular multiverse model, but to show that modern cosmology entertains structures much larger and more varied than the observable universe alone. These structures, if real, would reshape the question, is the universe infinite, into a more complex inquiry about the size, number, and variety of domains in a broader reality. At the same time, they highlight the limits of current knowledge. The evidence that supports them is indirect and tied to theoretical elegance and consistency, rather than to direct observation. The observable universe remains the only domain that can be mapped in detail. Whether it is the whole of existence or one region among endlessly many others, is for now an open possibility that keeps the question of cosmic infinity active and unresolved. From the perspective of the larger structures, the observable universe is a pattern of filaments, clusters, and voids that stretches to the edge of current maps. Within that pattern, the region containing the Milky Way is one part of a larger concentration of galaxies. On scales of tens of millions of light-years, the Milky Way belongs to a collection known as the local group, a small cluster dominated by two large spirals, the Milky Way itself and the Andromeda Galaxy, along with many smaller companions. On somewhat larger scales, this group is one of many such associations that gather into the Virgo cluster and related structures, and these in turn are part of a broader supercluster complex. The cosmic web seen in surveys passes through this region, as it does through many others, with filaments of galaxies and dark matter connecting dense nodes and surrounding large voids. From a distance, the local group is a point along one of those filaments. From within, it is the immediate cosmic environment. Following the path inward, the Milky Way appears as a nearly flat rotating disk of stars, gas, and dark matter, with a central bulge and spiral arms. The disk spans on the order of 100,000 light-years in diameter. Hundreds of billions of stars orbit its center, embedded in a much larger dark matter halo, whose extent is inferred from the motions of stars and satellite galaxies. The Sun is one of these stars, located in a minor spiral feature, sometimes described as a spur between larger arms. Around it, the solar system occupies a tiny volume compared to the entire galaxy. Planets, asteroids, comets, and dust move under the influence of the Sun's gravity, while the whole system orbits the galactic center over a period of hundreds of millions of years. On scales of light hours and light days, the solar system contains most of the matter directly relevant to the immediate environment of Earth. Beyond the outer planets, a sparse population of icy bodies extends outward, and further still, an even more diffuse cloud of comets may form a nearly spherical reservoir. All of this in turn moves through the interstellar medium and the broader galactic environment. Following the path further inward, Earth is a rocky planet orbiting at a distance where liquid water can exist on its surface under present conditions. Its thin atmosphere, magnetic field, and geologically active interior create a complex environment in which oceans, continents, and life have evolved over billions of years. From the standpoint of cosmology, Earth is a point-like object, far too small to appear on maps of the cosmic web. Yet, It is from this surface that all observations of the universe have been made so far apart from the small displacements provided by spacecraft. The question of whether the universe is infinite is therefore addressed from a very specific place in the hierarchy of structures, one galaxy in one small group, in one segment of a filament, in one observable volume of space. The path from the cosmic web down to Earth shows how each level of structure is nested within a larger context. The local group sits inside a filament which sits inside a supercluster region, which sits inside the observable universe, which may itself be only a small part of a much larger whole. At the same time, each level has its own characteristic scales and processes. Gravity binds stars into galaxies, galaxies into groups and clusters into superclusters. Within galaxies, gravity and other forces shape star formation, planetary systems, and local environments. On the larger scales, dark matter and dark energy control the growth of structure and the expansion of space. On the smaller scales, quantum mechanics governs particles and fields. These nested structures form a continuous hierarchy from local to cosmic, but the question of infinity only becomes prominent when the outermost layers are considered. At the level of the Milky Way, the issue is whether there are more galaxies beyond those currently known, and whether the background of galaxies continues without end. At the level of the observable universe, the issue is whether space itself has a global limit. Yet even when focus is restricted to local surroundings, the traces of the larger cosmos are present. The night sky as seen from Earth includes nearby stars, distant stars in the Milky Way, and faint galaxies that are members of the cosmic web. The cosmic microwave background, though detected with specialized instruments, rather than the unaided eye fills local space with photons that have traveled since the early universe. Each cubic meter around Earth contains relic radiation that carries information from a time when the entire observable universe was hot and dense. In this way, the local environment is suffused with signals from the larger structure. The question of infinity may be posed about the totality of space, but its evidence passes through a small region around one planet. The hierarchy of scales also influences how data about the universe are interpreted. Measurements of the cosmic microwave background are made from satellites orbiting Earth, yet they refer to conditions that prevailed when the entire observable universe was only a fraction of its current size. Galaxy surveys map millions of galaxies from telescopes on or near Earth, yet their conclusions about homogeneity and flatness apply to volumes billions of light-years across. The path from Earth outward is therefore also a path from local measurements to global inferences. At each step, assumptions about symmetry, representativeness, and the universality of physical laws are used to extend what is known in one region to what is thought to hold in others. This is necessary because direct access to distant regions is limited by light travel time and horizons. It also means that the question of infinity is approached through layers of reasoning that start from the immediate environment and move outward. The structure of the solar system, for example, shows how a finite system can appear effectively boundless to inhabitants without access to precise measurements. Early models of the cosmos place the stars at a finite distance on a celestial sphere around Earth. As knowledge expanded, that sphere dissolved into a three-dimensional arrangement of stars at widely varying distances, and the Milky Way emerged as a galaxy. Later observations reveal that the Milky Way itself is one galaxy among many. At each stage, the perceived scale of the universe grew, and regions once thought to be outer boundaries became internal layers. This historical pattern does not prove that the current understanding of the observable universe as a finite volume within a larger whole will necessarily be superseded in the same way, but it shows that the sense of being near a boundary can change as new levels of structure are discovered. From the perspective of the present narrative, the inward path from the cosmic web to Earth emphasizes that the infinity question is not detached from everyday scales. the same laws that govern local motions of planets and light also govern the behavior of galaxies and the expansion of space. Newtonian gravity gives way to general relativity at high precision, but the continuity between them allows measurements in the solar system to constrain cosmic models. Quantum effects underpin atomic structure and also generate the fluctuations that seed the cosmic web. This unity of physics across scales makes it possible to infer properties of the very large from experiments on the very small and from observations in the local environment. It also implies that if the universe is infinite in space or time, that infinity expresses itself through laws that are already familiar in local contexts. In this part of the story, the journey inward therefore serves two roles. It shows how the observable universe, with all its large-scale features, connects down to the immediate surroundings of a single planet. It also shows how the question of infinity posed about the largest structures depends on measurements and theories that are tested in that small region. The Earth orbits the Sun orbits the center of the Milky Way. The Milky Way moves within the local group, and the cosmic web and all of these motions unfold within an expanding space-time whose full extent is unknown. Whether that space-time is finite or infinite, the path from the larger scales down to the local environment makes clear that the infinity question is ultimately an attempt to understand the stage on which all these nested structures exist, from the most distant galaxies to the quiet space around Earth. By the time the discussion reaches the question of what can actually be concluded about the size and duration of the universe, a pattern emerges. Every major line of evidence points to a cosmos that is large smooth on the biggest scales, and governed by simple physical laws that hold across vast distances. The observable universe contains hundreds of billions of galaxies arranged in a web that extends to the limit of current surveys without showing signs of a boundary. The cosmic microwave background records an early phase in which this entire observable region was hot and dense with tiny fluctuations that later grew into the structures seen today. Measurements of curvature show that space is extremely close to flat. The expansion history shaped by dark matter and dark energy indicates a universe that has evolved over a finite but very long time, and that is likely to continue expanding for an immense future. Inflationary models suggest that the observable universe is a small part of a much larger region that underwent rapid expansion, and in many versions that larger region is either vastly larger than the horizon or effectively infinite. At the same time, each of these elements leaves crucial aspects unresolved. Flatness does not determine whether space is infinite or finite with a large characteristic scale. The existence of horizons ensures that only a finite volume can ever be observed from any given world line, even if space as a whole has no limit. Topology allows a universe to be finite yet edgeless, so that travelling in a straight line could eventually return to the starting point without encountering a wall, while still looking indistinguishable from an infinite flat space on all currently accessible scales. Inflation explains why the observable region is smooth and nearly flat, but does not uniquely dictate the global topology or total volume. Dark energy drives accelerated expansion and sets event horizons, but does not by itself decide whether the underlying space extends without bound. The hot Big Bang phase is firmly established as the earliest reliably described chapter in cosmic history, yet theories about what occurred before it allow both finite and infinite pasts. Multiverse ideas offer frameworks in which there can be many domains with different conditions, but they remain beyond direct test. Cosmic variance and the single vantage point limit how precisely global properties can ever be known. Together, these facts lead to a careful conclusion. Modern cosmology provides a coherent and detailed description of how the observable universe behaves. It constrains curvature, composition, and expansion with high precision. It offers mechanisms for structure formation, and suggest natural ways in which a very large, or effectively infinite cosmos can arise. It also reveals fundamental limits to knowledge imposed by horizons by the finite age of the universe and by the statistical nature of the data. Within these limits, the question of whether the universe is infinite does not have a definitive answer. Instead, there is a set of well-supported statements that any answer must respect. One statement is that the observable universe is finite in age and in the volume that has come into causal contact so far. Another is that within this volume the universe behaves as if it were part of a much larger, nearly homogeneous structure consistent with near-flat geometry. A further statement is that if the universe is finite, its total size must be much larger than the region that can currently be observed, because any strong signs of finiteness such as large curvature or obvious repeating patterns would likely have been detected. At the same time, an infinite universe is fully compatible with all available data, and many theoretical models naturally realize such a case. The decision between these possibilities depends on properties of space and time that lie beyond present observational reach. Future observations may tighten some of these constraints. More sensitive measurements of the cosmic microwave background and large-scale structure can refine estimates of curvature and test specific inflationary models. Deeper galaxy surveys can probe the cosmic web to larger distances and earlier epochs. Improved observations of supernova gravitational waves and other cosmological probes can sharpen the understanding of dark energy and its evolution. In parallel, advances in theoretical physics may clarify how quantum gravity behaves at extremely high energies and small scales, providing a more complete picture of the earliest phases of the universe. Some proposed signatures of non-trivial topology or multiverse interactions may be either discovered or ruled out more firmly. However, the presence of horizons and cosmic variants suggests that even with such progress, some aspects of the global structure may remain permanently hidden. The region inside any event horizon is a finite portion of whatever space-time exists in total. No instrument can retrieve information from beyond that limit. No experiment can directly sample more than one realization of the universe. These constraints are not artifacts of current technology, but consequences of the basic structure of space-time as understood through general relativity and relativity-based quantum field theory. They imply that while models can be tested against the observable universe, competing scenarios that agree perfectly within that domain but differ beyond it may never be distinguished empirically. Living with this situation means regarding cosmological models as frameworks that describe what can be observed and as tools that extend those observations into plausible descriptions of the unobserved, rather than as final maps of the entire cosmos. Some models will be preferred because they are simpler, because they fit the data with fewer assumptions, or because they connect smoothly to well-tested physics in other regimes. Others will be regarded as speculative extensions. The question of infinity sits at the boundary between these categories. An infinite universe is a natural outcome in many simple inflationary and flat geometry models, and it fits comfortably with the absence of detected boundaries. A very large but finite universe with subtle topology is also compatible with the same data. Multiverse constructions embed both options in even larger structures. None can yet be singled out as uniquely correct. From this perspective, the status of the infinity question is neither trivial nor purely philosophical. It is a scientific question framed in precise terms, grounded in relativity quantum theory and observations, yet shielded by limits that may never be fully overcome. The current state of knowledge allows clear statements about what the universe is not. It is not small compared to the observable region. It is not strongly curved on those scales, and it is not obviously bounded by a simple edge. It also allows a range of consistent possibilities for what the universe might be beyond the horizon, including finite and infinite structures. The inability to choose decisively among those possibilities with present data is itself a result showing where the frontier between what is known and what remains open lies. In this final step of the narrative before the story slows into rest, the universe appears as a system in which infinity is a live possibility but not a requirement. The observable cosmos is vast-structured and comprehensible to a remarkable degree. Its deeper extension, whether finite or infinite, remains uncertain. The edges of knowledge are set by horizons in space, by the finite age of the hot phase, and by the statistical nature of the data. Beyond those edges, carefully constructed theories describe how the universe might continue, but those descriptions are not yet anchored by direct evidence. The result is a state in which the size of the universe, in the strict sense of whether it is infinite or not, is an unanswered question that continues to motivate observation theory and quiet reflection, while the part of the cosmos that can be seen and measured remains a secure foundation for understanding how the visible sky has come to be as it is.